Hello everyone and welcome to some more reverse engineering learning. Today we're going to look at buffer overflow 0, 1 and 2 from Pico CTF. So we've downloaded the binary and the source for this first one and we can give it a look. So if we run it, asks for some input and then says the program will exit now. Nothing really too exciting, but we can have a look at the source code to find some more detail. So it looks for the flag in the local directory, sets up the signal handler, asks for the input and reads it into this buffer. As we know, sort of gets here is the dangerous part because it doesn't do any bounds checking for how much input you give to the destination, so it's not limited. That's our buffer overflow. And so in order to get the win here, there's this handler that will print out the flag when there's a seg fault. So all we have to do is pretty much fill the return address with garbage. So here's a sort of picture, the local buffer's here, some other variables don't matter, but we just have to fill it up so that this return address crashes and we'll get it. So the solve for this is pretty much that. We just make a buffer and a payload that exceeds the size of the buffer. And we just send it and that's it. And we just have to read it back. So we can go over here and run it on the remote to verify. There we go, perfect. That's the first one done. So the second one builds on top of them. So they all build on top of each other. So let's look at the next one. It's very similar, but now it looks like the more standard return to win sort of challenge, where we have this win function, the vulnerability section that even gives us a nice printout of where it's jumping to, and that's really it. So what we have to do is go the extra step further of, rather than filling it with garbage, this return address, we have to explicitly fill it with the return address of of the win function, the memory address of the win function. And so this is where I sort of decided to try and automate a bit more, and I recommend having a look at the Pwn Tools library, and there's some ways where you can start to automate this exploitation. So rather than creating this long string payload with cyclic that looks like this, and then stepping through the instructions with GDB to find out exactly where it crashes, we can automate some of this, which is kind of cool. We can go through and get it to run like normal, send it the payload, get it to crash, and then once it crashes, look at explicitly the incorrect address it tried to access and use that to help us find the correct offsets required. So we sort of see that here. So we run the process for the first time, create a payload of garbage using cyclic, send it, wait for it to crash, and then find the exact offset that's required. So the padding, this will give us the padding to go from our input to the return address, so we know how much space occupies this section before our known address. And so all we have to do then is, once we've calculated the offset, send the memory address of win that we want it to jump to. So let's go and fire that one up. Here we are, so change the port, and we can change directory. And there we go, so it's jumped to our win function, and here's the flag. Perfect. So let us go now to the last one. So similarly, this one builds upon it and goes an extra step, where this time it tells us we have to control the return address as well as the arguments given. And if we look at our picture for reference, we have again a local buffer, the return address, but then we also know after the return address are the parameters that are on the stack that are going to be used by in the next stack frame. So these will be referenced. So we can check that out. If we look here, it's almost identical, except that in this win function, it says there's some arguments here that are going to be referenced, and we have to check that they equal, cafe food and food. Perfect. So how do we solve this? Very similar, where we're going to do the same steps as before, let the program crash, find out where to calculate the offset, and then we have to go and append some extra information. So we can see the payload created, and we can see here is where we start to pack in this cafe food and food. But just something to keep note of is sometimes you'll get tricked up by the packing of these addresses. So the 32 and 64. So let's run it. Previously, this is what tripped me up for a little bit, was this address was packed as P64, but these values shouldn't be. So I'll just give you a little rundown of what went wrong. So I have a breakpoint set about like here in the C code, where it starts to compare these arguments. Oh, it's still trying to access the remote. Bear with me a second. Let me comment this out. And try to run that again. Okay, so it's against the local binary now. So we can see here it's starting to do this comparison of the static value cafe food to what's been given as an argument on the stack, and it's at EBP 0x8. So let's examine that. And so we can see here that this first one looks good. You can, if we step through the instructions, compare, next instruction, the jump not equal instruction is not taken because it satisfies it. But when we look at the next one, where it compares EBP plus, the address 0xC, or the offset of C, to this, we can see that it doesn't exactly quite line up. So if we look at that address, we can see it's hit those zeros instead. So you can see cafe food 0 and then food, and that's because of that packing of those hex characters. So just something that tripped me up, and you should be on the lookout for as well. So we can go and change that to use the 32, and then we can go run this against the remote. Change the port and tell it to not use the local debugging, and we can give it a go. Perfect, and there's our last flag for buffer overflow 0, 1, and 2. Any questions, let me know. Thank you.